Hello. Hello, hello. Hello, Paulina. Hello, Alan. Hello, Katie. Oh, she's at a disco. Okay. Hello, Paul. Hello. Sorry. Good afternoon, Claudia. I'm sorry. Okay, wait. I'm looking. I thank you for waiting. Sorry, she. Oh, Shy. I'm sorry. I had a student named She once. Okay, right. Good morning, Shy. Good afternoon, Emily. Good afternoon, Alexis. Good afternoon, Maria. I see you. Hello. Good afternoon, Victoria. Good afternoon, Alan. Good afternoon, Claudia. Good morning, Logan. We're in a good afternoon, Eric. Actually, he's not making a value judgment on the afternoon. He's just reporting the data. Okay. Good afternoon, Stephanie. Your camera's being bugged. Okay, yes, I was having technical problems too. I apologize for my lateness. Thank you for waiting. But yes, good afternoon, Katie, and good afternoon, Shirley, and good afternoon, Maria. Okay, that's who else did I miss? Okay, that's the video and that's the chat. Oh, why? My God. Okay. Um, okay. Let's just get all right. Sorry to be late. Let's just get to it. We're going to get to some new material now. I will. Thank you for those of you who did, like three of you did the extra credit finishing up from last Wednesday, which I really appreciate. But whether you did it or not, let me summarize quickly now. And again, I'm talking quickly because I just lost 5 minutes and all of that. But me talking quickly does not mean you cannot stop me. Maybe it means all the more reason you should stop me. Whether you sort of did that extra credit or not, you do want to know that the result, the summary, I guess I'll, yeah, do I want to, yeah, okay, I'll write this, okay, because you are responsible for this. So let me just be as clear as I can about what happened last time. And if there is something in the chat. Oh, good afternoon. Yes. Hello. Awesome. Good to see you. The last class was 29-22. Yeah. Okay. Okay. The big takeaway, and this is important, honestly, like it usually, I mean, not to, it's usually, it does appear on our final get together. So I want you to understand that for a mass on an inclined plane without friction, okay, without friction, just to simplify the issue for a moment, if an inclined plane is smooth and it's inclined at an angle of theta from the horizontal, the acceleration down the inclined plane of the mass will be g sine theta. Okay, that's so the acceleration due to gravity will be, and that means down it will be down. That acceleration will point down the inclined plane and be of a magnitude g sine theta, regardless of whether the mass is moving up the plane or moving down the plane. Like, I don't care whether the mass is velocitizing up or velocitizing down. Its acceleration will point down the plane and be of magnitude g sine theta. And the big takeaway from last week is that you can come to that conclusion whether you analyze the problem through a traditional coordinate system, like for which the x-axis is horizontal and the y-axis is vertical, or you can come to that conclusion if you tilt your coordinate system so that the x-axis lines up with the inclination of the plane. We get the same, and please write this down some way or another. And again, if you want to write it down and then like screenshot your notes and like submit for points, like if that helps, please do. Because again, this is like a big takeaway that due to Galileo's principle of relativity, whichever coordinate system we choose to analyze and solve the problem, whichever coordinate system we choose, we get the same correct physics answer, because the laws of physics are the same in all coordinate systems. We get the same physics answer, and the physics answer is A equals G sine theta. But one of those coordinate systems actually takes a lot less math, a lot less algebra, a lot, arguably even a lot less trigonometry, you could say, like certainly a lot fewer sines and cosines. One solution takes a lot less mathematical computation than the other solution, but it does require physical intuition. Like, I'm going to say this one more time. Like, in other words, if we don't tilt our head, if we don't do a physics technique of changing our coordinate system to meet the requirements of the problem, if we don't shift the coordinate system, and if we don't, I'm going to back up and say that again. If we do change our coordinate system, tilt our head, line the x-axis up with the direction of acceleration, and thereby break up the vertical vector mg into two components, mg sine theta and mg cosine theta. If we do all that, it takes physical, conceptual thought to do that. It doesn't seem natural. It doesn't seem natural to tilt our head. It doesn't seem physically natural to break up a vector that's already perfectly vertical. It seems it's a physical insight. It's a physical leap. It's a conceptual leap. It's an intuitive leap. It's like not the obvious thing to do. But by doing it, we reduce a huge amount of mathematical computation. We literally reduce the number of sines and cosines by from 3 to 1 in each equation that we do. So this is like a major example of the difference between physics and math. I'm not saying one is good or the other is bad or anything like that, but I'm saying that like the math part of physics is not what we're interested in as such. The math part of physics is the language of physics, but the physics thinking that helps us set up the math and in fact reduce the math and in fact keep the math as tidy as we can. The physics thinking that we're trying to learn here and that develops from Galileo's time through Einstein's time. The physics thinking is to choose our perspective to, well, the physics thinking is that physics works no matter what perspective or coordinate system or reference frame we choose. It works the same in all coordinate systems, but it's a lot easier to compute and to do. It's a lot more convenient in some than in others. So we choose our coordinate systems very consciously. We do things that don't always seem natural at first blush, but become natural after a while in physics. And bottom line, and the key thing here that we did, that we will continue to do in, say, Physics 204, if I hope you please join me in that course, the thing that we'll continue to do is, when faced with a Newton's law problem and a free body diagram situation and forces and all that, our strategy in general is that we choose an x-axis that lines up with the expected direction of positive acceleration. That reduces computations and sines and cosines and all that kind of stuff. That's the takeaway of this. Again, those people who finished the computation like last Wednesday and submitted it got points, and that's terrific, and I'm like really glad they did. But let me but I don't mean this to like separate them from everybody. And it was 3 people, so let me also say the reverse. I mean, there's 1,000 reasons. We're all very, very busy and all that, but it's not a total coincidence that like 18 out of whatever, that the remaining of you didn't choose to do that because it's a pain in the butt. Like that computation was so long and we didn't even finish it in class. Please take that as the takeaway. Like the reason we break up MG into MG sine and MG cosine is to avoid all those computations that we couldn't even finish by the end of class. Okay, but you are responsible for knowing those computations at least once. Okay, so that's okay. Oh yeah, okay, and I'm going to stop, and I don't mean, I'm going to look. I see there's things happening in direct chat, and really, I don't mean, and honestly, I so don't mean this to shame anybody that didn't do the extra credit. Like it really is not. In fact, since I'm not actually literally going over it right now, if you want to take another night, you could still do it. Those of you, if you were like right in the middle of it or want to ask me questions, I'm not saying I won't. I'm not going to take them forever, but I would take them again tonight or tomorrow or something like that. Like it's not a shaming thing. I especially because I am now explicitly telling you all, you do need to know that computation at least once. I mean, to be able to do it at least once to appreciate what we're really doing here with the physics. It never goes away. This physics idea, it's the basis of Einstein and everything of the 20th century. I'm about to look at the chat, but let me also say one other thing. Because this also came up in the last class. Also, please understand, like we evolved in this discussion from your lab assignment, which I think in this section maybe was due today. I can't remember, but it has started as an attempt for me to help you with your lab. And I hope I did, or I hope you understood your lab, and then went into this thing. Just to be clear, in your lab, friction was involved and friction played a huge role. In this whole analysis, I left the friction out because it's hard enough even without the friction, but it's not a contradiction, just to be clear. Everything I'm saying here in this analysis about the everything I'm saying here is about the gravitational contribution to the acceleration. And then you put friction in and all of this would still apply. It's just like yet another set of sines and cosines that make it even. So I guess that makes number 3, actually. I guess it was 1 to 2 without the friction, but that just makes another layer of extra math to deal with if you don't tilt your head. Okay, so I don't know if that makes sense or not, but I was just, for this analysis, the thing that, I would hold you responsible for later, I was just examining the role of gravity in an inclined plane. But then in the lab, because right from the get-go, you were tilting your head, it was believed that you could handle friction as well. All right, I'm going to look in the chat now, and then I'm going to go on, totally on. Oh, it's due on Friday? Oh, okay. Is that what I said? I didn't even know that. Okay, is that what I said? It's due on Friday? Okay. Wait, this Friday?
No, I was talking about the lab. It's due on Friday.
Oh, thank you. I'm sorry. Okay.
Because
Great.
last week was Thanksgiving, so it's not due till this week.
Oh, right. Okay, well, actually, thank you for that. All right. So Katie, thank you for that clarification. Because then if that's the case, I mean, given that is the case, then 2 things remain open. I will still take these extra credits. I will. Like, should I say till Friday I'll take them? Yeah, I mean, I guess I'll take them till Friday. I don't know if I'll remember to adjust it in the Google Classroom, but I will take these extra credits if anybody wants. I will. Although I'll also say now, okay, I'm going to say really quickly, I will take them. But if the people that handed them in right away that day, like I just looked to see if they did it correctly, if they knew what I was talking about, if it was talking, and basically gave them full credit. If you're going to do it now, please please, you don't have to do the whole 5-step method or anything. I get, well, because you're finishing something, but please at least still make the question clear at the top, make it totally clear what you're doing, and then totally box your answer at the bottom. Really make it clear. This is the issue. This is what I'm solving. Or this is where we left off in the competition in class. Like we were up to this point. Now this is what I'm doing. This is the answer. Like all of us need to practice all the time for all physics. Like every document you ever, because I'm still behind, as many of you know, in grading certain very important documents of yours. And there's so many documents that come to me. Like your job is any given document that you ever send to me, it itself should speak very loudly exactly what it is trying to do. And that's really good practice for publication, for research later in life. Like, just never assume that the person on the receiving end of your communication, like, remembers where you are in the conversation, if that, you know what I mean? And I actually do try to remember and do try, but okay. So especially if you're going to do the extra credit now, since I'm moving on in my mind, make it super clear what it is. Okay. But then as far as the lab, since Katie just said that the lab is due Friday, then that means, even though I'm going to move on now in a second, I am going to move on in the curriculum. I'm still happy if anybody comes up with a very specific, concrete question that would help them with their lab report. I'm still happy to try to help. Like, I want this whole course to be unified. So you could try it in the direct chat or whatever. And if I feel like it's a major derailment from what I'm saying, then I'll ask you to repeat it in text or email. But the door is not closed on me trying to help you. You get my point. Okay. Okay. And then the direct chat person who says they wanted to do it but got confused. But if it makes sense now, then please give it a shot. And if you direct chat person who's going to try to do the extra credit, feel free to reach out to me and I'll see what I can say. Okay. Last thing. So I'm going to move on. I'm going to move on to a totally new topic now. Okay. Or a topic that we definitely need for Physics 204. And you'll know that there's a homework now posted for next Monday, not for Wednesday. Like, you have a whole week to do it. It's kind of large, but the semester's not over yet. There's homework due Monday on the topic that I'm going to start dealing with right now. The topic is work and ultimately energy conservation. The topic really is energy conservation, but work is the first concept we have to establish in order to talk about energy conservation in physics. Of course, you've heard of energy conservation in many other contexts. Now we have to deal with it in physics. But I just want to also say, it says it in Google Classroom, but let me reinforce. The document somehow is very uneditable. The homework for work, it's very more uneditable than usual, and it's a little bit old. So any references to the textbook, please just ignore. I see them. I know they're there. I mean, if you happen to have a textbook, great. But like, don't, if it says to read something, or just ignore the references to the textbook. I'm aware that they're there, and I will make sure that you know everything that you need to know that it's okay. So don't worry about the references to the textbook. And in fact, and bear with me. So we're going to start now in this concept of work. And let me bear with me for one more second, because just bear with me for one more second. But if while you bear with me, if there's other questions, if I'm forgetting things, and I still owe some of you documents, I am very aware, not aware enough to have solved the problem, but they are coming. They are coming to everybody. I mean, to anybody who hasn't got one. Okay, just trying to move the homework up so you can actually see. Okay. I know you can't find the homework right now. Bear with me. Happy Thanksgiving, everybody, by the way. Okay. Okay. Okay, so here we go. I'm looking back. There's nothing in the chat. Okay. I'm going to start. So this is like a totally new, of course, everything in physics is connected. Okay. But this is a new topic, as new as topics get. The old topics never go away, but now we build something from the old topic. The old topic, the last topic was force, right? The relationship between acceleration and force. This topic is, or at least a subtopic, is work. So I'm going to start with a definition. Okay, now, this is the definition. This is not an easy. I'm going to read it in English. I'm going to break it down and say a lot of things about it. But just so you know, from now on, the work done on an object to displace it or move it from position x1 to position x2 is defined to be the integral of the dot product of the force exerted on that object with respect to its displacement. Obviously, I'm going to say that more than one time, and I'm going to say it also more than one way. But let me start by saying this. Well, I'm going to put it on the next page. Hold on. I'm going to write it again, so don't worry. I'm saying this. Okay. So this is a calculus concept. This is where the calculus really starts to get heavier, and it gets fairly heavy for physics 204 for whatever it's worth. So I'm zooming out and I'm going to zoom in on this definition. Okay. First off, I'm just telling you, and this is a definition. This doesn't come, well, yeah, that's funny. That's very fair and very funny what Maria just wrote. Oh, wait, did you write in that? Sorry. Oh, yes, she did. Okay. Or they did. Yes, and I'm glad someone had the guts to say, yes, this is a bit of a jump now, okay? And I have to warn you, and it's happening now at this point in the semester, because the honest reality is that physics 204, you really do have to start really dealing with calculus. So let's back up for a second. Like, I am well aware that there's a calculus prerequisite or two for these courses. I'm well aware of that. And I'm well aware that we keep referring throughout this course to things like derivatives in particular. We do keep, and we make a big point of the conceptual connection between, say, velocity and first derivatives. We make a big deal of the connection between acceleration and second derivatives. It is hoped that by having taken calculus or by taking it at the same time as this course, that the relationship between physics and that the relationship between these physical ideas and these mathematical ideas like gets reinforced by your work in physics to this point. But we're also very aware, believe me, that we haven't really asked you to solve much in physics by doing calculus. I know that. To some people, that's a relief. To some people, it's almost like a disappointment. Like, why did I have to do all this calculus to get in this class? And we don't actually do the calculus. We don't at first. At first, what we're showing you is the inside of the ideas of the calculus, which is really sort of motivated in many ways by many people from physics. But yes, it comes to the point where we start actually having to do calculus operations to solve physics problems. The point starts now. It is a jump scare moment in a way. And the point really kind of it really does sort of explode in physics 204, which is why we sort of trying to like accelerate a little bit right now. But I'm aware of all that. Like, and I could go on all day. Believe me, I have no illusions that most people by this point, most people by physics 204 have taken a lot of calculus and are not really in their hearts comfortable with any of it, or at least not a lot of it. I know that. We're not here to expect that you have a huge degree of comfort or command of calculus. We're here to expect that you have exposure and familiarity with calculus terms, and we're hoping that by the end of physics 204, you've actually used you've used the calculus enough that actually by the end of 204, you really do get it a lot better than you ever did before. Okay, so the transition starts now, and it starts, and I don't mean to overdwell on what Maria said, but it is hilarious and it's totally fair, and it may be what's in many of our minds if we're paying attention. We've been alluding to derivatives up until now and not really using them much. Now I'm all of a sudden going to integrals, and I am. Now I do plan on breaking down the idea of an integral to some extent, and I plan on breaking it down even more in 204. But I'm going to break it down by zooming in progressively. That is to say this. Well, hold on. That is to say this. Okay, this is what I mean by I'm zooming in. I'm saying from now on, work is the integral of force with respect to displacement. I mean, that is what I'm saying. And clearly, those of you who are somewhat comfortable with integrals, those of you who feel honestly in your heart of hearts somewhat comfortable with integrals already hopefully can get somewhat of a picture of what I'm saying. Like to some extent, I'm talking to those of you who feel somewhat in command of integrals. I'm saying we've got a new concept in physics now called work. What work is the integral of force with respect to displacement. Let me be even a little bit more specific. I'm saying if you treat displacement, if you treat change in position or difference in position from one place to the next, if you treat that as the independent variable, like the input, and you treat force as the dependent variable, the output, for those of you who can follow what I'm saying, and it will be everybody by the time I'm done, I hope, I'm saying that if you integrate force with respect to displacement, if you integrate force throughout some displacement, you'll get something that we call in physics work. Now, again, do I honestly believe that every single one of you in the room, even those of you who are totally paying attention, like, do I believe that everybody can now picture what work is just because I said integral? No, I don't. So I'm going to break it down further. And in the process, I'm going to be trying to do two things. I'm going to be trying to teach you what work is by explaining it as an integral, but also, just to be clear, I'm also using the physics concept of work to try to get across better to many of you what we ever meant by an integral in the first place. Because I will tell you this, one of the most vivid, clear, straightforward examples that we could ever picture in our mind for what an integral actually is the concept of work, okay? So we're going to do this for a couple of days, obviously. And it's going to come, it's the way we begin the physics 204s too. Like we're into the material now that sort of like we lift off from in physics 204. So bear with me. You could experience the calculus jump scare. Like, again, I'm like really glad that Maria actually like identified that for us, but don't let it scare you away. Take this is an opportunity for us to get actually to like confront the beast of calculus and start getting a little bit more comfortable with it. I'm going to explain what work is as an integral. Your goal can be either, it could be to understand work better by virtue of integrals, or your goal might be to understand integrals better by virtue of work, and both can feed each other. And honestly, that's how I learned all this material. I went round and around between the two until both of them got more and more clear to me. I didn't start with thinking that either of them was clear, just so you know. Okay, so I'm going to break this down for, oh, wait, so sorry, there's something in the chat, I think, unless I missed it from before. Oh, okay. Okay. So yes, that's cool. What Katie put in the chat. Okay, I totally want to, yes. I'm pausing just to wondering, I totally want to say something about that. I'm wondering whether I want to write something down about that. Give me a second. Yeah, actually, yes. Yes. So Katie wrote, this is like, oh, and yes, it's like a little bit like figurative what she's saying, but it's, yes, she's on point. She's saying this is almost like the inverse of how acceleration is the derivative of speed, like good connection. Okay, so hold on. Okay. So first of all, yes, acceleration is the derivative of velocity, and velocity is the derivative of position. Acceleration is the second derivative of position with respect to time. Absolutely. And we've been very concerned with acceleration. It's so concerned that then we went to this whole notion of forces and net forces and did all this analysis with net forces so that we could figure out what the acceleration of an object is at. Our whole focus has been, our whole focus has been that if we draw a free body diagram on an object, such as that, this is just an example right here, like of our most recent important free body diagram, right? But what the free body diagram, what does the free body diagram do? The free body diagram identifies all the forces that are acting on a point of mass at a point in space at a point in time. And the whole idea is that if you add up with vector addition and components and all that, if you add up all the forces acting on a point at a point in a point, if you know all those forces, then you know the acceleration at that point in time and space, right? It's a derivative because, like as Katie is saying, an acceleration is a derivative because it's like in the limit as delta t approaches zero. The whole picture of instantaneous rate of change, of position with respect to time. It's all about taking a freeze frame of time and space, getting the information from that freeze frame, and then inferring or concluding or extrapolating what must be going on in the larger movie of space and time. And I'm not exaggerating, right? I mean, I'm being figurative, but not really. If the goal of physics is to predict where something is going to be when, the whole model up until this point in the course, the whole idea is that if you focus all the attention on a point in time and space, you can get all this information about that point in time and space. And the information is called a derivative ultimately. Whether you're like doing calculus rules or not, what you're looking at is a derivative, right? And the belief. And so now you picture a derivative is like the analysis of a point on some curve in a graph, right? The whole idea is that if we get that acceleration, then we go back to things like a equals v minus v over t, or we go back to things like x equals 1/2 at squared plus v naught t, or blah, 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 blah. And from the derivative of the function, we then somehow know the whole function. We know the whole curve. We know the whole graph. From the information of the snapshot, we believe we can predict the future of the movie, or retrodict, the past of the movie. We're either making a prediction about the future motions, where something going to be when, or we're doing forensic science, we're doing criminalistics, we're like solving a crime, right? Either way, the belief up until now is if you get a snapshot of the present, then you know the future and the past. And I'm not saying any of that's wrong, by the way. It's like totally right. Like it's physics, but it's a derivative picture. I mean, to go now back to Katie's point, whether we're churning like product rules or power rules or quotient rules or not, what we've been doing is a derivative picture up until now. The derivative picture, is a model, is a way of analyzing at a point, right? Slope of the tangent line means slope of a curve at a point. And the whole reason we give a crap about the slope of the tangent line to a curve at a point is we believe if we know that, somehow we then know the rest of the curve. It's quite fascinating, actually, to me. But now we're going to go in the other direction, like Katie's pointing out, and like Maria warned us. Like we're going in the other direction. Now we're going to go to the integral picture of physics, the other side of the fundamental theorem of calculus. So we're going to look now. So now I'm saying this in English now. Instead of looking at what a force is doing just at a pixel or like at a snapshot or whatever, we're now going to ask, wait, what about a force acting throughout some finite continuous interval, like segment, like region of space? I'll put that in English now. We're now going to ask, we will ask, what is the effect of a force acting throughout a finite continuous region of, in particular, space? When we ask that question, when we shift our attention from force or from anything at a point to that same thing acting throughout a continuous region, then we're shifting our attention from the derivative to the integral. Okay? Okay. Sorry. Yes, absolutely. Oh, no problem. Okay. and keep these comments. I mean, I'm very glad people are. There's at least 3 people that are clearly engaged. Well, there's at least 4 actually, because I see video too. No, I'm sure many of you are, but yes, again, please, if you secretly look, again, I can't emphasize this enough, and this is true for a lot of physics 204. If secretly in your heart you've always sort of felt like you kind of do get calculus, or which means not just that you know how to do it, but you sort of get what it's about, then you now have, there's going to be, you're going to have maybe a easier time appreciating or understanding some of the things we're going to talk about from here on in. But if secretly in your heart you've always been a little bit uncomfortable with calculus, please view this as an opportunity to get more comfortable with calculus. It's not, we're not assuming that you've mastered it. Like, even, and frankly, I'll even be more blunt, even those of you who totally can do, who got A's and can follow all the rules and do all the procedures, I don't assume that that means that you actually understand it either. I mean, it goes both ways, whatever, you know what I'm saying? Okay. So what is an integral is what I'm trying to explain right now. Oh, got it. Okay. Okay. I'm going to try to build up this notion of work, and I'm going to try to build up this notion of integral sort of at the same time. So what I'm going to do is, first, I'm going to zoom down in my analysis. Maybe zoom is the wrong word, but I'm going to scale down to a small situation. And I'll tell you what I mean by small. Okay. I'm going to start by saying, let's first, before we get into the calculus, like I'm taking away the integral for the moment, I'm building it up. I'm saying first, let's examine an object that undergoes a small displacement, a small but finite displacement, call it delta x. In fact, you might want to make a note in your notes that from now on, I'm going to try to be pretty explicit. If I ever say delta anything, from now on, delta anything, say delta z, means a small but finite displacement, a small but finite difference from now on. If I ever say delta, yes, delta means difference, but specifically when I use delta from now on, I'm going to mean a small but finite difference between two values of a variable. This is illegible, I know. If I say delta anything, if I say delta z, I mean small but finite difference z2 minus z1. Here in this case, I'm saying delta x, I mean small but finite difference between x2 and x1. Okay, I will contrast that with an infinitely small difference in a few minutes, but that's what delta x means. So let's consider a small amount of difference So say we've got this block. And it moves this small but finite difference delta x. And why does it move that way? Because someone exerted a force on it. Let's say they exerted a force on it whose magnitude is F. Then what we're saying, and F would be measured in newtons, and delta X would be measured in meters. We're saying, we're just defining a concept now, that the small but finite amount of work that is done on this block to push it through a displacement of, or pull it through a displacement of delta X meters, will be the amount of force times the amount of displacement. And the result of that is going to be measured in a unit called a joule. So from now on, 1 joule will equal will equal 1 Newton of force times 1 meter of displacement. Okay. So, I mean, you know, if F is 5 Newtons and if the delta X, if the displacement is 3 meters, then the small amount of work will be 15 joules. Okay. That's in the simple, in other words, that's the simplest possible, smallest possible case of work. So in English, so far what I'm saying is work is the effect or the outcome or the result or the consequence of how much you interacted with a certain object and how much that interaction led to a change in that object's position, right? So work has 2 components. It's like how much you interacted, i.e. pushed or pulled, and how far the object got. It's displacement. I mean, it's right. So it's almost like you could say it. Well, yeah, that's what it is. It's how hard you pushed and how far the thing got. That's what work is. Note its multiplication. So if E and 0 times anything equals 0, right? So the whole idea of work is it's multiplication. The more the force, the more the work, the more the displacement, the more the work. If either of those 2 contributing factors is 0, then there's no, you know, if you don't push an object at all, you don't do work on it. If you do push it, but it doesn't get anywhere, you didn't do work on it. Okay. So it's like effort and result, if you want to think of it that way. Now that is in the simplest case. And again, the unit of measurement is called a joule. A joule, 1 joule of work is 1 Newton of force times 1 meter of displacement. I'll also add, well, no, I'll leave it at that. Okay, so that's in the simplest case. That's in the case when the okay. Now I'm saying I'm starting with a simple case and I'm going to blow up from there. There's 2 ways in which this case is simple. One, it's the small case. It's when the displacement is small, but finite. Now, I definitely have to expand on that in a moment. Yeah. But the second aspect of this that I also ultimately have to expand on is notice I picked a case where the force was strictly parallel with the displacement. Like you pushed the thing forward horizontally and the thing moved forward horizontally. Okay, both of those make this multiplication like straight up multiplication as straightforward as it can be. But what we're really concerned with in the long run is all of the more general cases where both of those assumptions can be relaxed. So I want to deal with them one at a time. First, I want to deal with what I mean by small but finite. Okay, so the first issue is I'm saying that this definition of work, only this definition of work that delta W equals F times delta X only applies when it's like delta X, when it's small but finite amount of displacement. Well, what do I mean by small? Like how small is small? I actually mean something very specific by small. What I mean by small is this. Okay, this is actually a really important definition. When I say that delta X is small, I mean that delta X is small enough for F, the force, to remain constant, to not have room to change. So delta X could be like a couple of millimeters, or it could be a couple of miles. I mean, depending on the context. But what I mean by using a delta X is as long as the delta X is small enough in context that there's one number for F that doesn't change, then this definition applies. In other words, then in that case, we don't need calculus or integrals or anything like that. Like calculus, specifically, calculus comes into play when we have continuous variables, when we have things, quantities that are changing continuously. If there's no change in F, there's no need for calculus. Okay, so that's the first thing I'm saying. So yeah. So let's stay with that for a second. Wait, well, I'm just looking at the time. Well, yeah, actually, okay. Okay. So first of all, as long as you have reason to believe, so specifically, These are all equivalent, all the things I'm saying right now. I'm saying if f is a constant function, like I'm saying if f doesn't, delta x has to be small enough for f not to change. I specifically mean for f not to change as a function of x. If f does not depend on x, or put another way, if f is a constant function of x, if no matter what value of x, and remember, x is where an object is, if no matter where it is, over here or over there, if the same push or pull is being applied to it, if the graph that you would make of f being the dependent variable and x being the independent variable, if that graph were a horizontal line, then this whole definition is true, and the original definition is true, but there's no need to do calculus. It's literally a plugin. For work will be force times displacement, okay? And by the way, since we have 14 more minutes, I think most, if not all, I think the homework that you're doing for Monday is called work done by a constant force. So in all these, no matter how long the homework looks or no matter how complicated it looks, it's not actually a calculus homework as such yet. Okay, so just to note that, like, so you can rely. So far, all I'm really saying is that work is force times displacement. 1 joule of work is 1 Newton of force times 1 meter of displacement. However, okay, and we're going to expand more and get into the calculus more like on Wednesday. But that's what I'm saying right now. However, there's also assumption number 2 that we have to deal with. I think that was homework 9. Sorry, what was the homework that it doesn't really matter actually, but it's homework. Oh, it doesn't even say. Oh, it's homework 9. Sorry. Okay. Now, yeah. Okay. But now I want to deal with the other assumption. Okay. So question number, or assumption number 2, what I have to deal with now is what if we push or pull what if we displace an object by pushing or pulling it in a manner that is not perfectly parallel with its displacement? In other words, kind of like the child sled problem from before, or kind of like gravity on an inclined plane. Okay. right? What if we have one of these type of examples we've been looking at before where you have a 4, oh, and I should say, I'm sorry. What if you have an object that is displaced from one position to another, but I gotta say, sorry, the videos are so, the people that are showing video, like it's so clear they're paying attention. I'm just saying, it doesn't mean that the people that aren't showing video are not paying attention. I know that, but it's just like so clear that the people who are showing video are paying attention. I just say, so thank you. I'm just saying thank you. And I'm not thanking anybody else, but just note that for the record, it like makes such a difference. Okay, anyway, I'm just saying, so thank you, people. All right, anyway. So what if we have a situation where you're moving something, and that's what this is all about. This is all about pushing or pulling something so that it moves. That's like the entire concept of work, is you push or pull something so that it moves, right? So, but what if the way it moves is not the way you pushed or pulled it, like, which happens all the time. Like you could, like for leverage's sake, you could pull up on a string at some angle and get a sled to move horizontally. Or you could pull vertically, like you could be planet Earth, pulling vertically down on an object that doesn't move vertically, that moves on an angle. Like, how do we deal with that, right? And the answer is we do need to deal with it with some degree of specificity. There's 9 minutes left, I'm aware. Because presumably when a child pulls us, and I'm not even dealing with friction or anything like that yet, but like when a child pulls up on a slant, on a piece of string, in order to displace a sled through a horizontal region of space, like there's a reason the child is pulling up on, or the whomever is pulling up on an angle, but the reasons have to do with like the fact that the person is tall and the sled is short or whatever. If you pull on an angle, you're pulling some extent horizontally and some extent vertically, and presumably the vertical aspect or the vertical component of your pull isn't really contributing directly to the horizontal displacement, right? And we somehow want to take that we want to recognize that fact. So the first thing we recognize is force is a vector. It has direction, right? And displacement and also has magnitude, but displacement is a vector. It also has direction as well as magnitude, right? The question is, what does it really mean to multiply two vectors? How do we do multiplication when vectors are involved? We've actually never done this before. It turns out there are three ways to perform the act of multiplication when vectors are involved at all. Okay, in 7 minutes left, I'm going to address two of them. Well, I'm going to list all of them, but we're going to really care about one in particular. First of all, like, okay, I know we have 5 minutes left. First, I want to establish something about vectors. Say you've got two vectors, A and B, like they're each an arrow with size and direction, and they're random, like they have two randomly different sizes and two randomly different directions, okay? And say that they differ in direction by an angle of theta. Say theta is the acute angle between the tails of these two vectors. I'm just saying, right? So in general, you have two vectors that are pointing in different directions. And they're known as A and B with arrows over them because they're vectors. First of all, I want to say from now on, if we're in a vector context, if we're talking about vectors, so I write A with an arrow over it, I mean the whole vector quantity, the magnitude and direction. But if I just write A from now on, in a context like this, it's not a typo. If I just write A, I mean the magnitude of the vector A. I mean just the size, like, so to speak, the absolute value of the vector. Okay, that's we use double absolute. When we use double absolute value signs in vector land, we mean magnitude. Okay, so A without an arrow means the size of the vector A. Okay, so say, and same thing with B. So say I have two vectors A and B, and C is just some random number, or maybe C is the magnitude of some third vector C that I don't care about. Then there's three ways that multiplication could occur in such a vector context. And I'm going to like lay them out, and then obviously class is going to be over. I'm aware of that, and that's okay. One, we could have a scalar multiplied by a vector. And if we have that, like the simplest way, and I am watching the clock, I promise. The simplest way to do multiplication when vectors are involved is to multiply a vector by a scalar. When we do that, we always get a vector. Multiplying a vector by a scalar literally means taking an arrow of a certain length and a certain orientation and just changing its length, right? That's why these numbers are called scalars. In other words, if you walk 3 miles at 45 degrees to the northeast and we multiply that idea by the number 2, then you've walked 6 miles in a direction of 45 degrees to the northeast. When we multiply an arrow by a pure size, we just literally scale up or scale down the size of that arrow, but we still have an arrow. Okay, so multiplying a scalar by a vector always yields a vector. But the second way the more important way here is we could take two vectors together and produce a scalar. And that's what we're doing in this context with 2 minutes left. And this is called, if you could do scalar multiplication of two vectors. That means multiplying two vectors together in a way that yields a scalar result. This is called the dot product of two vectors. And this is where I'm going to land for today. By definition, the dot product of two vectors, A and B. Remember, two vectors, random vectors, A and B, that are separated by an angle theta. The dot product of those two vectors is the magnitude of one vector, i.e. the length, times the magnitude of the other vector, times the cosine of the angle between them. Okay, and we have 1 minute left, so let me just, well, yeah. So, and this is what we do in the case of work. A little bit of work is the dot product of a force vector with a displacement vector. The idea is you take the size of the force, you multiply by the size of the displacement, and then you multiply by the cosine of the angle between them. Because what the cosine measures is how parallel they are. That is, and of course I'll pick up on this on Wednesday, but remember the cosine of 0 is 1, and the cosine of 90 degrees is 0. So if a force is purely, if the angle between a force and a displacement is 0, then you multiply the force times the displacement and then times the cosine of 0, which is 1, you get 100% of the work done. But if you were to exert a force perpendicularly to a displacement, you would do no work whatsoever. And anything in between is a number that gets bigger and bigger as you get closer and closer to parallelism. So I'm ending with this, but I'm saying that in a small amount of displacement, the work we do is the magnitude of the force times the magnitude of the displacement times the cosine of the angle between them. Because what we're really asking is, we're really saying it's how much of the force that is parallel to the displacement. We're only multiplying the component of the force that is parallel to the displacement. We're multiplying those two numbers together, and that's how we get work. I'm going to pick up on, and then there's a third way to multiply vectors too, but we don't do that so I'll pick up on all of that on Wednesday. In order to do the homework or start the homework, you actually have now everything you need. Well, most things, but anyway, we'll continue on Wednesday. Okay, and I'll hang out here for any questions or anything, and there is something, but have a great day. Oh, have a good one. Yes, okay, thank you. Have a great day. Okay, and I'm turning off the record, but I will be here. Thank you. Great day. Okay. Have a good one. Okay, you guys all good? Okay. And you're good, Shawnee? Are you there? Or you're good? Going once, going twice.